Stoichiometry can be done using a BCA table very nicely. It allows you to understand what's going on in a chemical reaction, how the recipe component of it works, how it doesn't work. What we want to do now is show you an alternative calculation method that you can use if you're looking for a little more speed in your calculations and understand the BCA table and kind of the logistics behind this, and you're ready to move on to something quicker. So the process for this starts by finding your given. So we're going to do two examples here. Our first given is 24.5 grams of nitrogen. We do need the balanced reaction right now, just like we would in a BCA chart. What we're going to do is we're going to write that down. And it's really important to put the unit and the chemical throughout the whole thing. If you leave out one, then you're going to end up getting confused. And you're going to draw a really long line like this. It's going to work as a fraction bar. What we're going to do is we're going to do a set of conversions that are kind of repeat over and over and over again as we change different things. And the first one is just like in a BCA chart, we're going to change from grams to moles. So you need to be in moles to be able to work out this relationship between nitrogen, hydrogen, and ammonia. But we also need to keep in mind that we're working with nitrogen at this point. So we're going to change from grams of nitrogen to moles of nitrogen. Now when we're going from grams to moles, we're using the periodic table, and we're going to do 1 mole of each chemical per how many grams it says in the periodic table. So for N2, we would take 14.01 for each nitrogen. It would come out to be 28.02 grams of nitrogen. So go ahead and rewrite that so we got all of it nice and neat. 28.02 grams of nitrogen is equivalent to 1 mole. Now when we multiply 24.5 grams of nitrogen by 1 mole of nitrogen divided by this molar mass, what we're doing is we're canceling out the units and creating a new set of units. But we're also multiplying by 2 equivalent values. So we're not changing the quantity or like how much it's worth, we're just changing the unit. So the number changes and the unit changes, but the amount stays the same. So we would take 24.5 grams times 1 divided by 28.02, and that would tell us the moles of nitrogen. But before we plug that in, we're going to continue on and we're going to do some more conversions. So this next step, we're going to change from moles of nitrogen into something. Now when you're starting with moles in your conversion, you're going to change to the moles of the chemical you're seeking. So in this case, we're seeking out ammonia. So for that, we're going to use the coefficients from the balanced reaction. So nitrogen has a 1 next to it, and ammonia has a 2 next to it. So just like we did in the BCA table, that kind of comes into play right there. And then the last step is we're going to change that from moles of ammonia back into grams to get a gram value. So again, now we're looking at a periodic table relationship. Every 1 mole would be 17.04 grams of ammonia. So what we do then is we'd multiply 24.5 times 1, which is itself, times 2 times this. And we divide that answer by this, and then we have 1s the rest of the way. And so that comes out to be 29.8 grams of ammonia. For sig figs, we would have the same sig figs as we started, 3, so we're good on that. So let's go ahead and do one more really quickly. Let's look at the second one here. We have 8.30 grams of hydrogen. We would start by writing that down. We'll draw a really long line. Really important to always keep the units and the chemical there. So we're going to take grams of hydrogen and convert it to moles. So and I'm rounding these molar masses to 2 decimal places. You might do that differently based on your teacher. But every 1 mole would be 2.02 grams of hydrogen. Then we go ahead and do our molar masses. So we're looking at moles of hydrogen converting into moles of ammonia. That again, we're pulling off of this reaction. So we've got 3 moles of hydrogen, give us 2 moles of ammonia. Okay, and then our last step, we can go ahead and copy off here for the most part. We're changing 1 mole of ammonia into grams, 17.04 grams of ammonia. Okay, so again, what we do is we would now go through and we would say 8.3 times 1 times 2 times 17.04. We divide that answer by this times this times this. So we're going to divide that by 6.06. And that comes out to be 46.7 grams of ammonia. Now at the point where you've done both of these problems, what you can now do is you can actually go back and do a little analysis, and you can figure out which one will run out, which one will have excess, so on and so forth. So what we could do now is we could go back and look and say, okay, we can only make so much ammonia with the nitrogen. We can only make a little under 30 grams. So when we get to this amount of product, we're going to run out of nitrogen. So we'll know that if we mix this amount with this amount, instead of with excess for each, we could actually compare, and we could say that in that case, this would have been our limiting reagent. The hydrogen would have been in excess. This would be the amount of product would form, because at that point the reaction would stop. And we can also go through and plug in and figure out how much excess we would have by doing a ratio of the two answers. If we take 1 minus this ratio, 29.8 over 46.7. So this ratio gives us the kind of decimal form of the percent of how much the reaction occurs. So 1 minus that will be how much doesn't occur for this reaction. So if we multiply that by 8.30 grams of hydrogen, then we'll end up figuring out how much excess we would have. So if I divide 29.8 by 46.7, that comes out to be 63.8%. So 63.8% of this hydrogen gets used up, and therefore if I subtract that from 1, then I have 36.2% left over. So 36.2% of 8.3 comes out to be that I have 3.00 grams of hydrogen remaining in excess. So if we look, I mean, we're looking at about a 2 to 3 ratio here, 30 to 45, a little bit less than that. So we're looking at about 2/3 of this gets used up, so about a third left over, and so 3 grams makes perfect sense for that. So this has some advantages, especially if you get into later chemistry. You might want this so that you can do things faster. If you're looking at electrolysis and coulometry, this could be convenient for doing analysis. The BCA is better to understand at the moment. It's better to understand at the introductory of chemistry, but this can also be useful later on.